Okay, welcome back. So we are now on 15th of October 2021, and this is Linear Algebra Part 2, Chapter 7. So I will go through the introduction of least squares, but before I do that, I would like to point out to you the relevant videos in strengths video. You can start from lecture 14, which talks about orthogonal vectors. A dot B is equals to 0 and the forming of subspaces. After that, you can go through projection onto the subspaces, which we have done. Projecting a vector onto a line. And then later on, you'll realize that we can now project a vector onto a space. And when we learn about projecting a vector onto a space, we'll be going into projection matrix and least squares. So I would also, in today's lecture, go through in this process, what does this mean? But I watch strengths lecture and I find them to be very, very good. So if you have a chance, you just watch these 3 or 4 videos, and then maybe you can then look at our lectures and then see and hopefully understand it better. Now let's begin. So I'm recording this now, and so if you have any questions, just type into the chat. Right, let's start. Now we begin with the simple problem of this, what we did in lecture 1 is that we are given 2 equations and 2 unknowns. And here 1x1 plus 0x2 equals 1, 0x1 plus 1x2 equals to 2. And we are asking you to solve. And of course, visually by inspection, you immediately know x1 is equals to 1 and x2 equals to 2. But let's just pretend that we do not know how to do this. And then we are going to continue to do it in what we have did in the past, which is we write 1, 0, 0, 1 to represent this matrix, these coefficients. And then we have x1 here, x2 here. And then we are representing 1, 2. And then, of course, we didn't have to do Gaussian elimination. Typically, you have to do Gaussian elimination. But because we are already in reduced row echelon form, and you can identify the pivots, and then we can then do back substitution and we solve. Then to reduce row echelon form, and solve by back substitution. So this is what we did in the lecture 1, and we know how to do it now. And here it's very clear that so observation is that this problem has a solution. What does has a solution means? Imply that if we call this matrix A and this vector X and this vector Y, then what does this having a solution mean? Then we can find a vector X that satisfies AX equals to Y. So that's what by having a solution means that there is such a solution and AX will be equals to Y. All right, I'm going to throw a spanner in this equation, and I'm going to introduce an additional what do you call that? An additional equation. So from this example, now we are given an additional equation. And this additional equation is 1x1 plus 1x2 equals to, okay, so guys, please help me out. if I want to have the equation satisfying the new equation satisfying the above solution, what must this be? Can you all type onto the board, please? Onto the chat. 3, of course, because you know that x1 is 1, x2 is 2, 3. But now I'm going to throw a spanner in this and say it will be 6. And it will lead, so this will lead to a system of inconsistent equations. And then we're still going to try to solve it. All right, but let's continue to proceed. So I want to change my matrix into this form now. So I'm going to write it here. My original matrix is 1, 0. Second equation is 0, 1. Third equation is 1, 1. And this is still my x1 and still my x2. And my equation is still 1, 2. And my new equation given to me is 6. And now, of course, if you perform Gaussian elimination, what do we get? So the only interesting thing is the last equation. So by Gaussian elimination, what we do is we do it this way. And of course, this is a dotted line. And on the right-hand side is the 1, 2, 6. Okay. Now, what am I going to do? I'm going to take the third equation. So row 3 equals to row 3 minus 1 times row 1. Then after that, the new row 3 is equals to the new row 3, okay? Is equals to row 3 minus 1 times row 2. So what do we get, guys? All right, I'll do it. So this row, so it will be 0, 1. First, 6 minus 1 is 5. Then one more time, 1, 0, 0, 1. The last row minus the second last row is 0, 0, 3. So this shows us that 0x1 plus 0x2 equals to 3, which is nonsense because, you know, it basically demonstrates that there is an equation that is inconsistent with the rest. And when we reach this point, implying there is no solution. So this is what we learned in tutorial 1. Now, but if we stop here, of course, then we'll never get anything done because most likely equations given to us are inconsistent. So when we reach here, we want to do something called least squares. What can we do? Well, let's call this still A, and this is still Y. We want A x equals to y. I mean, that's what we have been trying to do all the time. But we know that if the system of equation is not available, what we can do is if inconsistent equation, then the best that we can do in this course, okay, it's called the least squares solution. By least square, it means we find a x hat, so not x anymore, and it will not be equals to y anymore. We call it y hat, and then plus e. So what we want to do is such that y hat plus e is equals to y. That's because we still want to get y, and the norm of e, the length of e is minimum. So the cool thing about this is if this is all satisfied, then we still get y hat, which is an approximation of y. We get E to be the smallest that we can get. And all we are trying to do is to find a x hat, x hat. Now, if you look at this very carefully, what is the interpretation of this? So okay, I don't want to confuse you first. So I'm going to this. We're only trying to do this. We're only trying to do this. Ax hat equals to y hat. Okay, the E here is not, so we cannot approximate E because, you know, basically that's all. We can't, right? We cannot approximate E given A. So what is Ax hat? What is the interpretation of Ax hat? So this interpretation, please interpret carefully. This interpretation is equals to y hat is a linear combination of A. Because if you look at the algebra, it is, let's call this A now. U1, U2. Let's call him U1 and U2. And our A, remember this is our A, is nothing but a 3 by 2 matrix equals to 1, 0, 0, 0, 1, 0. This is our 3 by 2 matrix of A. And therefore it is nothing but U1 times X1 plus U2 times X2. Sometimes I put a dashed line below to show you that they are vectors, and X1 and X2 is the vector X in this AX hat. Okay. All right. So Y hat is a linear combination of A, implying that Y hat belongs to the column space of A, right? This is obvious. This is what we say. AX hat equals to Y hat. Therefore, Y hat is a linear combination of columns of A, and therefore Y hat belongs to the column space of A. And yes, later on, Aidan will ask how to get X hat, and the answer is the orthogonal projection. So let's see the picture of orthogonal projection. So if you have the Lay's book, then you can turn to this page. And in this, the green space here is the column space of A. A times X can reach any point in this green space. B is our Y, okay? B is our Y. So we want to find a point on the space such that it's the nearest to B. We can move it anywhere. We can, if A times X1 reaches here, A times X2 reaches here, A times X hat reaches here, right? Because you basically find any linear combination. X1, X hat, X2 are different. You reach different points. Geometrically, it is obvious that when we reach this point, it is the nearest. Why is it the nearest? Because the length, this dashed line represents the error E. The error E is the shortest when the error E, and the word is orthogonal to the space of column space of A. So we're orthogonally projecting B onto the column space of A. Okay, so that's where we are trying to reach. All right. Now, let's continue to now. Let's come back to here. in this problem, although what do you call that? Although we cannot solve this using the tutorial one's approach by Gaussian elimination and back substitution, we can solve it by our chapter 6 approach, orthogonal projection. The columns of A, U1 is orthogonal to U2. We can then use theorem 6 in our lectures to project Y onto the column space of U1 and then Y onto the column space of U2. Let's try. Okay. So first, I'm going to draw the pictures for you. So I'm now in number 4. And let me try to remember what is our A here. It is 1, 0, 0, 0, 1, 0, and our Y is equals to 1, 2, 3. We would draw our picture now, and we'll draw this one first. So this is 1, 0, 0. This is the origin. We'll now draw this. And then notice that they are orthogonal to each other. This is 1, 0, 0. This is 0, 1, 0. So let's call this the U1. And let's call this the U2. U1 dot U2 equals to 0, implying U1 is orthogonal to U2. All right, what about, where's the last space? Actually it is here. So this is 0, 0, 1, but unfortunately we don't have that. What is our Y? Y is 1, 2, 3. So let's draw 1, 2, 3 here. So this is 1. This is 1. This is 2. This is 1. This is 2. This is 3. So it will land so this is Y equals to 1, 2, 3. And now I'll draw a line here in green. Okay. Right. So you will realize that it is now obvious that if I only have U1 and U2, my linear combination is only the plane, the horizontal plane on the floor, and my Y is up there at a height of 3. But so if I geometrically to solve this problem, it is obvious that if I can pick any point in this space, the nearest point to Y is this point. This point in, let's say, red color. And this point, we can even read it off because the bases are orthogonal. We can just read off 1 and then read off 2 at the second axis. And it is obvious that the solution is 1, 2. And because I cannot reach anywhere on the vertical axis, all I can get is 0. And this is Y hat. Okay, now do you all have any questions why in the geometric fashion, I will be able to choose immediately that this point is my nearest point, okay? And then I can write it this way. Because you realize that my basis doesn't have a vertical element in it, so I can never go up. I can only go horizontally along here or horizontally along here, 90 degrees. And the best I could do is to get 1, 2. So I get Y hat. Now, Therefore, E, let me make some space. Therefore, E, the vector E here is equals to, so it is, if this is E is equals to Y minus Y hat. So the error E, the vector along the orthogonal projection, is E equals to, this is Y minus Y hat. This is Y hat. So now I choose the different color again. So this is Y hat in green. So my E is therefore 0, 0, 3 is my E. This is equals to 1, 2, 3 minus 1, 2, 0 equals to Y minus Y hat. Now, so, but we figure out what is Y hat, guys. Y hat equals to 1, 2, 0. So what is A? X hat equals to Y hat. What is X hat? So we write our A again. 1, 0, 0, 0, 1, 0. X hat equals to 1, 2, 3. And of course, there's nothing for you to do because it is so obvious, right? Because you can see it. You can say that x1 equals to 1, x2 equals to 2, and you can see it. But let's say, okay, so you can solve it now for, I mean, sorry, this I should put 0. What am I talking about? This is Y hat. So you can solve it. Now the system of equation is consistent. 1, 0, x1, x2 equals to 1. 0, 1, x1, x2 equals to 2. 0, 0, x1, x2 equals to 0. So when what we are doing in the graphical way is that we are forcing our Y hat to lie in the space of the column space of A. And since it lies in the column space of A, the equation must be consistent. So this is an artifact. Yeah? This is due to forcing Y hat to be in the column space of A. So this last line here, right? If you compare it with our previous last equation that had made the system of equation inconsistent. And now when we solve, it's trivial. All right, so this is how we solve it in our, what do you call that? Our lecture number chapter 1. In chapter 6, we solve it differently. Given the basis is orthogonal, we apply theorem number 6. Let me check. Theorem number 8. And if the basis is orthonormal, we apply theorem number 10 in all this in chapter 6.2.5. So let's go and see these lecture notes first. In 6.2.5, we go to theorem number 8, which is here. And again, it says, if now is W. W is a subspace. In our picture previously, the subspace is formed by the column space of A. Same thing. Here also says that the nearest point of Y onto a point in W is the projection of Y into W. And in our tutorial 6, if W given to us, if W is spanned by an orthogonal basis. So here's the key point. If W is spanned by orthogonal basis, then Y hat simply I project Y onto U1, Y onto U2 until Y onto UP and sum it up. So let's see this method. Okay, so I will write the equation first. I'm going to write this equation for our purpose. So the equation is Y hat equals to Y dot U1 over U1 dot U1 times U1 plus Y dot U2 divided by U2 dot U2 times U2. So in our example, I only have YU1 and YU2. Okay, so this is the equation. Now, so let's identify this on top here. This guy is U1 and this guy is U2. This guy is our Y. So let's, by brute force, make this happen. Y dot U1. Okay, I'm just going to do, where's my Y? Just going to write my Y here. And then it is 1, 2. This is not Y, sorry. I'm confusing myself. My Y is, remember where's my Y? My Y is 1, 2, 3. So 1, 2, 3. Dotting with, what's my U1? Okay, U1 is 1, 0, 0. Dividing by 1, 0, 0, dotting with 1, 0, 0 times 1, 0, 0 plus, then the second term is again 1, 2, 3, dotting with 0, 1, 0 divided by 0, 1, 0, dotting with 0, 1, 0 times 0, 1, 0. Okay, now it looks very complicated, but it's actually quite trivial. This returns that something dotting with something is a scalar. Something dotting with something is a scalar. These are very nice because they are actually, these U1s are normal, octonormal. So in fact, I should have used theorem 10. Okay, I'll show you theorem 10 now. Where's my theorem 10? Theorem 10 is, in fact, not this equation, but this equation. The bottom of it disappear because U1 dot U1, if the length of U1 is 1, U1 dot U1 is 1. So the difference between theorem 10 and theorem 8 is that thing in the bottom. That's all. Okay. So, and of course, in a concrete example, you also see that 1, 0, 0 dotting with 1, 0, 0 is 1. 0, 1, 0 dotting with 0, 1, 0 is 1. So when the bases U1, U2 are all normal, the bottom thing is reduced. So what I should have done was that I should have thrown this away and used theorem 10. All right, so let's continue with our brute force. 1, 2, 3 dotting with 1, 0, 0 is, so it is 1 multiplied by 1, 0, 0 plus 1, 2, 3 dotting with 1 is 2 multiplied by 0, 1, 0. So what do I get? It is obvious, of course, this is 1, 0, 0 plus 0, 2, 0. But actually, and then the answer is 1, 2, 0 as expected. But I don't like it to show it this way. I would rather you actually from here convert it into matrix form, and you will see that this is the original columns of A, and the found value, the coefficients is 1 and 2. Okay, and then we have the answer equals to Y hat. All right, so we found two ways, right, guys? We saw two ways to solve for Y hat. the graphical way where we sort of know that if we can see in 3D, then this point is closest, and this was 1, 2, 0. And by reading off the axis, we also know. Then, of course, we did the Gaussian elimination way. We also can see that the answer is, by back substitution, is 1, 2. And in the third way, we can see the theorem 8 and 10 is used to find 1, 2. Okay, so we saw it in 3 different ways. And of course, this was very easy to use because I have given you the solution, what do you call that? The problems with orthogonal basis. Now, I'll try to spend the next 15 minutes to tell you another problem. And this problem is this. Okay, so now I'm in page 5. Almost the same problem, okay? All right, so page 5. I would print this out, so don't need to copy, and then I would share this with you. Now, the problem is, so now we have example 2. The equations is reduced into 1, 0, 0. So this was, the first equation is 1, 1 multiplied by x1, x2 is equals to 1 again. All right, so our systems of equation have changed, huh? 1. But our y is still going to be 1, 2, 3, okay, guys? So this is y. Our systems of equation is 1, 1. That means 1x1 plus 1x2 equals to 1. The second equation is 0, 2. So 0 times x1 plus 2 times x2 is 2. And the last one, 0. Oops. So basically, again, I have given you a system of equation is inconsistent again. Okay, and then you say, hey, isn't this problem exactly like the previous one? No, because although the y is the same, these two guys are not orthogonal anymore. They are not orthonormal, they are not orthogonal. They are something. All right, so how? Now, so let's do it graphically again. This is U1. Oops, what is the color I use? Blue. This is U1. Let's call this U1 again, and let's call this U2 again. And let us draw the column space of the matrix A. Again, we have 1, 0, 0, which is nice. It is exactly like that 1, 0, 0 here. But U2 is not 0, 1, 0 anymore. They are not perpendicular in exercise 2. So I'm going to draw. So this is U1, which is equals to 1, 0, 0. What about U2? 1, 2. So I'm going to first draw the original U1 first. So let's say this is the original U1. Sorry, original U2. 1, 2, 0. So it's 1, 2. Okay, so let me draw the U2 in dark green. So it's 1, 2. So this guy is U2. U2 is equals to 1, 2, 0. Compared to the O, this compared to the O guy, this guy is 0, 1, 0, for example. So now I'm given two vectors, and they are not orthogonal to each other. So this angle is not orthogonal. Okay, so let's erase this, and therefore I cannot apply the what do you call that, the orthogonal decomposition. All right, but my y, where's my y sitting? My y is still sitting at 1, 2, 3. So let me 1, 2, 3. Where's 1, 2, 3? This is my y, which is 1, 2, 3. Where should it land? It should land here. Again, y hat should be equals to 1, 2, 0, because that's the closest point. Y hat should land in 1, 2, 0. Because why? My columns U1 and U2 is still sitting on the floor, the horizontal plane. The closest point that I can reach Y is still 1, 2, 0. So this is very illuminating, because what you'll see is that the solution that I'm trying to get must still be AX hat equals to Y hat. My Y hat still is 1, 2, 3. Sorry, 1. My Y hat, Y hat is still 1, 2, 0. So my A now is of course changed. My A is now 1, 0, 0 and 1, 2, 0. So what's my X1, X2? Again, if you realize that my Y hat needs to be 1, 2, 0, because again, any linear combination, I'm still sitting on the floor, on the plate, on the floor. Now my columns of A has changed. The only way you can get 1 to 0 is setting x1 to be 0, x2 to be 1. So that's the graphical way. Therefore, solution is x1, x2 equals to 0, 1. Because then you would see that x 0, 1 would be equals to 1, 2, 0. Now, this is a graphical way to solve the problem. But of course, we are never going to give you R3 and R2 problems to solve. So Oliver asked, what happened when we're not? So this is the least squares solution that I'm going to try to tell you. So this finally reaches the least squares. So we are now in 910, and we are going to reach least squares. All right. Now, so how do we solve if what do you call that, more more strategically, okay, right, let's look at the E. E is still E is Y minus Y hat. What is E? E is 1, 2, 3 minus 1, 2, 0 is equals to 0, 0, 3. Remember the characteristic of E? E is orthogonal to any vectors on what? Can someone tell me? E, the vector E is orthogonal to who? Right, please?
The column space of A.
Correct. The column space of A. E is orthogonal to the column space of A, to any vectors on the column space of A. Right, so let's see. So we start. So I will now derive the normal equation for you. So I'm in page 6 now. E is orthogonal to the column space of A. And how should I derive this for you? Okay. What is E? E is equals to y minus y hat. What is y hat? Y minus ax hat. And then after that, E dot who? E dot the column space of A is equals to 0. This is the E is orthogonal to column space of A. So y minus ax hat dotting with the column space of A equals to 0. How do we express this? What is the column space of A? So the column space of A is the set of vectors u1, u2, in this case only. How do you write this? It is, how do you do something dotting the other one? It is nothing but u1, I should write it this way. I should say u1 transpose y minus ax hat equals to 0 for the first equation. And the second equation is u2 transpose y minus ax hat equals to 0 to show that they are orthogonal. How to see these two equations, u1 transpose u2 transpose is A transpose. Y minus ax hat equals to 0. You open it up, A transpose Y minus A transpose ax hat equals to 0. So we have derived the normal equation. What are we trying to solve? We are trying to solve x hat. A transpose ax hat equals to A transpose Y. We just bring this guy across to the other side. We want to now get rid of A transpose A. If A transpose A inverse exists, then pre-multiply on both sides. On both sides. What do we get? A transpose A inverse A transpose A x hat equals to A transpose A inverse. Wait, I made a mistake. I didn't make a mistake, sorry. A transpose Y. This guy becomes the identity, therefore x hat equals to A transpose A inverse A transpose Y. So this is the famous equation, solution for least squares. So Oliver, you ask how to solve for x hat. This is the equation to solve for x hat. So now I will show you where it is. So it is in chapter 7. Where's my equation? Where's my equation? Sorry, guys. I gotta find my equations first. Hmm. 7.1.2, 7.1.3. Ah, there. So this is theorem 14. 14. A transpose A inverse A transpose. We use Y, he used B, X hat. So this is in 7.1.3, page 4, and we are done. Now, I still have 16 minutes. I'll pause now to take questions.